Azizan, the ID 99 is there or no? Yeah, so please share your slide. Unmute yourself. Just a moment. I can make you the, what you call that, the co-host. Just a moment. Give me a moment. I also make you co-host. I also make the co-host to you. If anything, you can manage, okay? Yeah, Usman.
Okay.
Okay. Then the fourth presentation will be given by Azizan from the School of Chemical Engineering, College of Engineering, University, Teknologi, Mara. She will be talking about oil palm from pretreatment box design optimization strategy using Emimac as ionic liquid for bioenergy potentials. So the floor is yours, please.
Thank you very much to Professor Osman for the brief introduction about me. Thank you to everyone. Good day to all of you coming from all over the world. Thank you again for still staying for the presentation today. I will present the work on the oil palm frond pretreatment using ionic liquid for the bioenergy potential, focusing on the design optimization strategy. I'm Azizan from the School of Chemical Engineering, College of Engineering, Universiti, Teknologi, Mara, Shah Alam, Selangor, Malaysia. So the pathway routes for the bioenergy, as seen here, shared by Lee Enterprises Consulting Incorporation, United States, showing you the various feedstocks which are available coming from the oil crops or the lignocellulosic biomass. In other words, I would say LCB, in producing different kinds of fuel, for example, the HVO, the hydrotreated vegetable oil, or the renewable diesel, the drop-in diesel. And if it's coming from the lignocellulosic biomass producing the ethanol or butanol, we could call it bioethanol or butanol. So what we would like to see today is what happens in the pretreatment itself. So Mr. Lee again shared the other various feedstocks coming from fats and oil and LCB. And you can see here there is no oil palm waste, oil palm plantation waste, but we could add there because they also share the same processing methods, producing particularly the same fuels and chemical types. Malaysia is the second largest country in the world producing the crude palm oil production, as reported by Umar and other authors in 2021, based on kilotons in 2017 after Indonesia. Mr. Goh in 2010 reported that a majority or the most of the percentage of the waste, palm oil plantation waste coming from the OPF, palm oil frond or oil palm frond. Next would be the EFB, empty fruit bunch, 18%. And lastly, 11% of kilotons in 2007. So this shows that the palm resources having high potential of producing bioenergy. For Malaysian case, Idris and other co-authors in 2021 in their paper on the assessment of the impact of intensive palm oil based bioenergy deployment, showing you different demand sectors, demanding sectors in Malaysia, coming from the sector of power, heat and transportation. And you could also again see that the various types of feedstocks for the bioenergy. And again, we would see the various types of oil palm plantation, which are highly potential, other than the rice, straw, or rice husk, and manure. Interestingly, those lignocellulosic biomass could be directly pretreated to produce bioethanol. I would elaborate on that later on, other than the pre-processing techniques that we have to undergo. So what do we have in the LCB itself? As you see on the slide, main contribution of the LCB is the cellulose, whereby according to the report by Go in 2010, for OPF itself, about 62% of cellulose contained in the LCB, other than the hemicellulose and also the lignin. Lignin is a little bit more complex, having the aromatic rings, and the cellulose has a very long D-glucose subunits, high polymeric chains, and hemicellulose a little bit shorter. So what we would like to use or present today is about the cellulose itself and the use of cellulose for the bioenergy. Sultanian and co-authors in 2020 presented on the many kinds of pretreatment process as shown on the slide, including the solvents used. What we would like to share with you today is the combined pretreatment, combining the many various types of pretreatment with the ionic liquid, which is assumed to be as the green solvent. Sultanian reported that we could try or venture alkaline with the ionic liquid, or the ionic liquid with the ultrasonic, apart from only using one kind of pretreatment processes. So what is ionic liquid? Agabawi in 2016 reported or wrote an article entitled Ionic Liquid Pretreatment as Emerging Approaches for Enhanced Enzymatic Hydrolysis of the LCB itself. It says that with the pretreated biomass, with the ionic liquid, is capable to produce the bioethanol as an emerging green solvent. There are two kinds of hydrolysis that could be ventured, either the multi-step hydrolysis or the one-step hydrolysis. With the multi-step, we need to go through the washing step to regenerate the cellulose before going through the hydrolysis process to produce glucose and ferment the glucose to produce bioethanol. Whilst the one-step process, we don't need to wash the pretreated biomass, whereby it will be directly used in the enzymatic hydrolysis using the ionic liquid compatible cellulase prior to the fermentation in producing the bioethanol. So there are various kinds of advantages of the ionic liquid itself. The first one would be it is proven to be non-toxic to enzyme or the enzymatic hydrolysis or fermentation. It could be operated in a low temperature, no decomposition of the cellulose. It has chemical stability with a low viscosity, which is good during the enzymatic hydrolysis or the fermentation. And finally, it could be recycled and reused. Unfortunately, at the moment, the cost of the ionic liquid itself, some of them are still relatively to be very expensive, but some of them are getting cheaper and cheaper, but relatively still very expensive. In this article by Agabawi, they investigated various kinds of LCB using the ionic liquids, and it's proven to be effective. So what do we have in the ionic liquid? It contains the cations and the anions, as shown on the slide here, shared by you, 2017. And the mechanism of the cations and anions during the pretreatment is that it is capable, or they are capable in destructing the intra and also intermolecular hydrogen bonding of the cellulose. In this case, it allows better dissolution of the cellulose so that it has a higher accessibility for the enzymatic hydrolysis in the next steps. In LCB itself, as you see on the slide shared by Puti, 2016, and Trashe, 2020, showing you the crystalline regions and also the amorphous regions. In other words, we could say that the crystalline region is orderly and the amorphous region is kind of disorder. So during the pretreatment process, the ionic liquid, for example, is capable to disrupt the orderly structure of the crystalline, producing, and also the amorphous region, solving it. And it is reported that the crystallinity index reduced due to the pretreatment with the ionic liquid. So as a start, we would like to know the optimized condition using the ionic liquid itself, because it's kind of costly still. And we started with the preliminary experimental investigation in a very low reaction volume of only 1 milliliter. First, we tried with 3 kinds of oil palm plantation waste, which were the EFB, OPF, and OPT. Later on, we introduced the OPF itself in the RSM method, and the software suggested us to run 15 sets of experiments combining 3 parameters, which we chose. So Azizan in 2020 reported the pretreatment various reactor model dealing with the microscale, macroscale, and also a little bit bigger than the microscale in reactor, the various parameters, engineering parameters that we need to look into. For example, shaking diameter, shaking frequency, reactor volume, reaction volume, temperature, pH, and many other parameters as well. So these are some of the engineering parameters that need to be optimized. So for this investigation, we chose to fix some of the engineering parameters and vary the EMIM acetate concentration, the solid loading of the sample or the OPF, and the temperature of the reaction mixture in a kind of a little bit bigger reaction mixture of 70 milliliter in an isothermal reactor. As you can see here are the 3 types of results for OPF, EFB, and OPT from the FTRR, showing that all of the pretreatment process as the concentration of the EMIM acetate increased. Again, this is preliminary results showing the reduction of the lateral order index and the crystallinity index. This is where you can see it more clearer on this slide using the Segal equation and O'Connor equation for the crystallinity index and lateral order index respectively. So you can see here that the LOI and CRI were reduced from the raw to 50% of the EMIM acetate concentration and from 50 to 100. Same goes to EFB and also OPT. So I'm going to go back to my previous slide showing you what happens from the FTRR results. As the concentration of the EMIM acetate increases, you can see that the peaks for various peaks references disappear. So it's something happens. So I'm going to go to this slide showing you the few functional groups in reference to the wave number. So if we were to calculate the LOI, we took the value of the transmittance, absorbance, we just simply translate it or convert it to transmittance at the wave number of 1,430 to the 898. Mainly, overall, you could see that the stretching and the vibration of the beta-1,4 glycosidic linkages. I forgot to mention when we at the slide showing the LCB in the cellulose, there is, I'm going to go back to that slide showing you the linkage here. So the important linkage here, which is the beta-1,4 glycosidic linkage, connecting between the D-glucose subunits. So what happens there? From the FTRR, we could see that the stretching and vibration occurs, allowing lower crystallinity index of the pretreated biomass. So from the slide, you could see clearer the beta-1,4 glycosidic linkage, which refers to the cellulose, as shown by the various wave number. So we also have a closer look via SEM, showing you, of course, there were changes after being pretreated with the 100% of EMIM acetate for OPF and EFB and OPT, showing more cracks and disordered structure and loosening of the surfaces in comparison to the earlier images, which were smoother and orderly and more compact. Now, looking at the SRD results, there are two peaks which are very important, the crystalline and non-crystalline. As the concentration of the EMIM acetate increases, the peaks slowly disappears, and you could clearly see, which I presented recently in another conference, but this was on the microcrystalline cellulose, the crystalline cellulose pure, the pure MCC. As the EMIM acetate increases, the peaks just disappear and became a flat line. And from the calculation of the Segal equation, the crystallinity index simply reduced. Now, for the strategy of the optimization using the Box Behnken from the RSM method, we want to make sure that the chosen low, medium, and high parameters for the three engineering parameters that we chose earlier are within the or inside the experimental region. Having the suggested standard runs by the RSM, giving us the combinations of EMIM acetate concentration, the solid loading and temperature suggestions. So we started with the experiment and calculated the CRI. If you can see here, the response surface plots showing you for the EMIM acetate concentration with the parameter of temperature and OPF solid loading are within the experimental region, which is good. And we could finally conclude that the optimization parameters that we could initially take into account, considering the optimized temperature of lesser than 100, the EMIM concentration, the EMIM acetate concentration, which is you don't need to use it until 100% pure, but you could choose until 48% or 50% volume to volume, and the solid loading 12% approximately. And what is interesting is that from the significant value, according to the p-value, if the value is lesser than 0.05, it is to be assumed statistically significant. From here, we could say that the solid loading OPF percentage values is not significant because it's larger than 0.05, but it is crucially important for the EMIM acetate concentration and also temperature for the pretreatment on OPF. For the future perspective, to take note that the preliminary optimization determination is only valid for a very preliminary data range, and we would love to extend it, of course, for a broader range of temperature and concentration of the EMIM acetate. And of course, we need to quantify the bioenergy capability with the OPF. So before I end my presentation, I would like to give my acknowledgement to the Ministry of Higher Education Malaysia for the grant, and also the School of Chemical Engineering, College of Engineering, UITM, Shah Alam, Malaysia, and also to FRIM, Forest Research Institute, Malaysia, because for the first part of the preliminary data before the optimization, we use the sample of EFB, OPT, and also OPF from FRIM. Thank you so much. So if you, I'm very looking forward to hearing any comments from the floor. Thank you.
Yeah, thank you very much for the presentation. And we have 3 minutes for question, if any questions. Okay, if there is no question, then we thank Azizan for this good presentation.